Students, in this video we are going to start the second chapter, analytic functions. Function, in which first topic is functions of a complex plane. S be a set of complex numbers. We see what is the definition of function. Let A and B two non-empty subsets of the set S. Then the rule F, which associates every element Z belongs to A with one or more element omega belongs to B, it's called a function or mapping from set A into set B. Means what? F is a function from A to B. If for every element Z belongs to A, there exists one or more element omega belongs to B, such that f of Z is equals to omega. Okay. Then we say that f is a function from A to B. Okay. This element omega is called the image of Z under F. Okay. And this set A is called domain for the function f. Next definition is the set f of Z such that Z belongs to A is called the range of f. Okay. See next, as the values of the function are complex numbers, so it is called a complex valued function or a function of complex variable defined on set A. Okay. Next definition is single valued and multiple valued function. The function omega is equals to f of Z is said to be single valued if for every value of Z there corresponds one and only one value of omega under f. Otherwise, it is called a multiple valued function. Okay. For example, omega is equals to f of Z. It is a single valued function, but omega is equals to f of Z is equals to root of Z is a multiple valued function. Yes, see students, why f of Z is equals to root of Z is a multiple valued function? Because if you take Z is equals to 4 here, so you will get f of 4 is equals to root of 4, and we know that root of 4 is plus or minus 2. Therefore, it is a multiple valued function, and f of Z is equals to Z. It is a single valued function. Let us see notation. Let omega is equals to f of Z be a function of complex variable Z is equals to x plus iy. As the values of omega is equals to f of Z are complex numbers, so omega will be the form u plus iv, where this u and v are the functions of real variables x and y. So omega is equals to f of Z can be written as u of xy plus I into v of xy, because u and v are the functions of real variables x and y. This can be written as u plus iv, where this u of xy is called real part of f of Z and v of xy is called imaginary part of f of Z. And this real part is denoted by this, and imaginary part v of xy is denoted by this. Okay. Let us see example. First example is find real and imaginary parts of the function. This is a function. We have to find real and imaginary part of this function. For this, we have to just put Z is equals to x plus iy and simplify this. We will get this is a real part and this is a imaginary part. So we will get u of xy denote real part. So u of xy is equals to x square minus y square plus 2x plus 2. And imaginary part is v of xy is equals to 2xy plus 2y plus y. Okay. let us see note. F of z is equals to this if the polar coordinates, we know that polar coordinates are r and theta, instead of x and y are used, then f of z u plus iv, it can be written as f of r into e raised to I theta, where z is equals to r into e raised to I theta. This is a polar form of complex number, and omega is equals to u plus iv. F of z can be written as, here we have using polar coordinates r and theta instead of x and y. That's why this f of z becomes f of z is equals to f of r comma u of r comma theta plus I into v of r comma theta. Okay, let us see examples. Find the real and imaginary part of f of z is equals to z square. F of z is equals to z square, which is equals to x plus iy square, which is equals to x square plus 2ixy minus y square, which is equals to x square minus y square plus 2ixy. So real part of f of z is this, and imaginary part of this f of z is this. Okay, when polar coordinates are used, means what? We use r and theta instead of x and y. So z becomes f of r into e raised to I theta, which is equals to r into e raised to I theta square, where z is equals to r into e raised to I theta. This is equals to r square e raised to 2I theta. So r square into e raised to 2I theta is nothing but cos 2 theta plus I r square sin 2 theta. Okay, so therefore u of r theta means real part of f of r e raised to I theta, which is r square cos 2 theta, and imaginary part is r square sin 2 theta. Okay, let us take next note. F of z is equals to u of xy plus I into v of xy. Call this equation 1. Okay, and f of z is equals to u of r theta plus I into v of r theta. If in either of the equations 1 and 2, the function v always has value 0. In either equation 1 and 2, if this v is 0, then f is always real. Okay, that is f is a real valued function of complex variable when v is 0 in either equations 1 and 2. For example, f of z is equals to mod z square is a real valued function, since f of z is equals to x square plus y square plus I 0, because here imaginary part is 0, therefore f of z is equals to mod z square is a real valued function. Okay, next, if n is 0 or positive integer, and if a0, a1, a2 and so on up to an are complex constants where an is not equals to 0, the function p of z is equals to a0 plus a1z plus and so on plus an z raised to n is a polynomial of degree n. Okay. Next is domain of this definition is the entire z plane. Questions p of z upon q of z of polynomials are called rational functions and are defined at each point z where q of z is not equals to 0. Example, let z denote any non-zero complex number. We know that z raised to 1 by 2 has two values. Z raised to 1 by 2 has two values. Z raised to 1 by 2 is equals to plus or minus root of r exponential of I principal argument upon 2. This notation is for principal argument. Okay. where r is nothing but modulus of z, and this principal value lies between minus pi and pi, is the principal value of argument of z. But if we choose only the positive value of this plus or minus root of r, and we write f of z is equals to root of r exponential of I into principal value upon 2, where r is greater than 0, and this. Next is the single valued function 3 is, this is now single valued function 3 is well defined on the set of non-zero numbers in the z plane. So here is 1. That is f of 0 is equals to 0, since root of 0 is equals to 0. The function f is defined on entire plane. Okay. Let us take example. For each of the functions below, describe the domain of definition that is understood. Means what? We have to describe domain for the given function. Okay. First example is f of z is equals to 1 upon z square plus 1. This function is defined everywhere in finite plane except at the points z is equals to plus or minus I. Means what? If you equate z square plus 1 is equals to 0, you will get z is equals to plus or minus I. Means what? If you put denominator equals to 0, your denominator equals to 0 at point z is equals to plus or minus I. This function is not defined. So it is defined everywhere in finite plane except the point z is equals to plus or minus I. Okay. Next example is f of z is equals to argument of 1 upon z. This function is defined throughout the entire finite plane except for the point z is equals to 0. Okay. Next is f of z is equals to z upon z plus z bar. This function is defined everywhere in the finite plane except for the imaginary axis. Why imaginary axis? See here, z plus z bar. If you equate denominator equals to 0, what will we get? Z plus z bar is equals to x plus iy plus z bar is x minus iy. Here plus iy and minus iy cancel, so we will get 2x is equals to 0. That implies x is equals to 0. Means at x, this function is defined everywhere in the finite plane except for the imaginary axis. Okay. In imaginary axis, this function is not defined. Next is f of z is equals to 1 upon 1 minus mod z square. This function is defined everywhere in the finite plane except on the circle mod z is equals to 1. Why? Because if you equate this denominator equals to 0, you will get mod z square is equals to 1. Mod z square is nothing but root of x square plus y square bracket square is equals to 1. Squaring on both sides, you will get x square plus y square is equals to 1. And this is nothing but mod z is equals to 1. So this function is defined everywhere in finite plane except the circle mod z is equals to 1. Okay. Take these two examples for homework. See this third example. Suppose that f of z is equals to x square minus y square minus 2y plus I into 2x minus 2xy, where z is x plus iy. Use the expressions x is equals to z plus z bar upon 2 and y is equals to z minus z bar upon 2y to write f of z in terms of z and simplify the result. Means what? Here you have given f of z this. You have to put values of x and y in terms of z and z bar, and you have to find the f of z in terms of z. Okay, take this example for homework. Next topic is limit of a function. Let f be a function defined on the subset S of C except possibly at z is equals to z0. Means what? F be a function defined on subset S of a C in deleted neighborhood of z0. A complex number omega 0 is said to be a limit of f of z as z tends to z0 if for given epsilon greater than 0, however small, mod of f of z minus omega 0 is strictly less than epsilon whenever 0 is strictly less than mod z minus z0 is strictly less than delta. We write it as limit z tends to z0 f of z is equals to omega 0. Okay, we say that limit z tends to z0 f of z is equals to omega 0. Okay, next theorem is uniqueness of limit. If limit z tends to z0 f of z exists, then it is unique. Let it possible, L1 and L2 are two limits of f of z. As z tends to z0, let epsilon greater than 0 be given. By definition of limit, there exists delta 1 and delta 2 greater than 0 such that, use definition of limit here, mod of f of z minus L1 is strictly less than epsilon by 2 whenever mod of z minus z0 is strictly less than delta 1. And if L2 is the limit of function f of z, then mod of f of z minus L2 is strictly less than epsilon by 2 whenever mod z minus z0 is strictly less than delta 2. We have to choose delta is equals to minimum of delta 1 comma delta 2. Then equation 1 and 2 hold good for delta in place of delta 1 and delta 2. Now consider modulus of L1 minus L2, which is equals to mod of, here add and subtract f of z. So we will get f of z minus L1 minus f of z minus L2. I will take f of z minus L2 in one bracket and take minus sign here common. So I will get f of z minus L1, which is less than or equal to modulus of f of z minus L2 plus mod f of z minus L1. So this is strictly less than epsilon by 2 plus epsilon by 2 by equation 1 and 2. Okay, and we know that epsilon by 2 plus epsilon by 2 is epsilon. So this modulus of L1 minus L2 is strictly less than epsilon. But epsilon is arbitrarily small positive real number, and modulus of L1 minus L2 is a non-negative number. It shows that modulus of L1 minus L2 equals to 0. So we will get L1 minus L2 is equals to 0. That implies L1 is equals to L2. Okay, means limit is unique. Limit of a function is unique. Now see one example. If f of z is equals to z upon z bar, then we have to find limit z tends to limit z tends to 0 f of z. Solution: limit z tends to z0, f of z does not exist, since we get 0 by 0 form. Okay, if you put here z is equals to 0, and so we will get 0 upon 0 form. But when we choose z is equals to x0, x order pair x comma 0 is a non-zero point on the real axis. So we will get f of z is equals to x plus I0 upon x minus I0, which is equals to 1. So here, when we take z is equals to order pair 0 comma y is a non-zero point on the imaginary axis. So we will get f of z is equals to 0 plus iy upon 0 minus iy, which is equals to minus 1. Okay. Therefore, letting z approach the origin along real axis, we would find that desired limit is 1. Okay. When z approaches to real axis, we will find that limit z tends to z0, we will get 1. Okay. An approach along the imaginary axis would minus 1. Means here limit z tends to z0, we will get minus 1. Since limit is unique, limit is always unique, so limit z tends to z0, f of z does not exist. Okay. Next, see theorems on limits. Suppose that f of z is equals to u of xy plus I into v of xy, where z is equals to x plus iy, and z0 is equals to x0 plus iy0, omega 0 is equals to u0 plus iv0. Then limit z tends to z0, f of z is equals to omega 0. If and only if limit order pair xy tends to x0 y0, u of xy is equals to u0, and limit v of xy as xy tends to order pair x0 y0, which is equals to v0. Means what? If f of z is equals to this, then limit z tends to z0, f of z is equals to omega 0. If and only if limit u of xy is equals to u0 and limit v of xy is equals to v0, as x order pair xy tends to order pair x0 y0. Next theorem is, suppose that limit z tends to z0, f of z is equals to omega 0, and limit z tends to z0, f of z is equals to w0. Then limit z tends to z0, f of z plus or minus f of z is equals to w, this omega 0 plus or minus w0. Next is limit z tends to z0 of f of z plus or minus f of z is equals to omega 0 into w0. C is limit z tends to z0, f of z upon f of, this f is a capital, f of z is equals to omega 0 upon w0. But when this is possible, when w0 is not equals to 0. Next is limit z tends to z0, f of, sorry, limit z tends to z0, z is equals to z0, and limit z tends to z0, c is equals to c, because this c is a constant. Okay. Next is limit z tends to z0, p of z is equals to p of z0, where p of z is the polynomial. Okay. Next topic is limits involving the point at infinity. First theorem is, if z0 and omega 0 are points in the z and omega planes, means z0 is point in z plane and omega 0 is point in the omega plane respectively, then limit z tends to z0, f of z is equals to infinity if and only if limit z tends to z0, 1 upon f of z is equals to 0. Second is limit z tends to infinity, f of z is equals to omega 0 if and only if limit z tends to z0, f of 1 upon z is equals to omega 0. Moreover, limit z tends to infinity, f of z is equals to 0 if and only if limit z tends to 0, 1 upon f of 1 by z is equals to 0. Sorry, here is infinity. Students, see here examples. Observe that limit z tends to minus 1, iz plus 3 upon z plus 1 is equals to infinity. How this is? Limit z tends to minus 1, 1 upon f of z is equals to 0. This is by property, means in theorem part 1 we have seen limit z tends to z0, f of z is equals to infinity if and only if limit z tends to z0, 1 upon z, 1 upon f of z is equals to 0. So we will get 1 upon f of z, okay, which is equals to limit z tends to -1. So here z plus 1 upon iz plus 3. If you put here -1, so you will get -1 plus 1 upon something is -1 plus 1 is 0, and 0 upon something is 0. So 1 upon f of z is equals to 0. That's why limit z tends to -1, iz plus 3 upon z plus 1 is equals to infinity. Let us see next example. Limit z tends to infinity, 2z plus I upon z plus 1 is equals to 2. Why? See here, we will do this example by using this second part. Limit z tends to z0, f of z is equals to omega 0. If and only limit z tends to 0, f of 1 by z is equals to omega 0. So here we will replace z by 1 by z. So I will get 2 by z plus I upon 1 by z plus 1, which is equals to limit z tends to 0, 2 plus iz upon 1 plus z. Means if you simplify this, you have z tends to 0, 2 by z plus I upon 1 by z plus 1. If you simplify this, you will get 2 plus I upon z upon 1 plus z upon z, as limit z tends to 0. Here z cancel. So 2 plus iz upon 1 plus z remains 2. As z tends to 0, you will get this limit is 2. Okay. And let us see next example. Next example is limit z tends to infinity, 2z cube minus 1 upon z square plus 1 is equals to infinity. We will solve this problem by using this third part of theorem. Limit z tends to infinity, f of z is equals to infinity if and only limit z tends to 0, 1 upon f of 1 by z is equals to 0. So here we will take 1 upon f of 1 by z. Okay. So simplify this, you will get this limit equals to 0. Okay. Okay, we will stop here. Thank you.